I have another question though. Does refraction affect on EDM signal for the same way as line of sight, i.e. robot with auto pointing on a target versus a human pointer?
Yes. Like any more than that? Remembering that what the robotic total station is doing is taking and scanning the return signal. And if it's being returned by a reflector, then there's a very strong signal from the center of the reflector, and it gradually diminishes as we look away from the center. So eventually it drops off quite dramatically as we get to the edge, and we could almost call it a Gaussian distribution where the peak is at the middle of the reflector and it falls off, and then quite dramatically as we get farther away from the center. And that peak is the same type of thing as if we were to look through with our eye. We're looking at the light that is coming off, say, the target or the center of the reflector. We're viewing it with our eye with respect to the image of the crosshairs, but it's still taking the center of the telescope. And basically the difference is that the human eye has been replaced by a quadrant CCD, which figures out from the imbalances where the center will be. So if it sees one quadrant that's stronger than another, it reacts to that until it's balanced amongst all four quadrants, and therefore is in the center, which is the same as what we do when we move the two tangent screws to center the crosshair. So it's the same influence. And that's pretty well discussed to some extent in the Whittaker paper, where they're using robotic total station, which of course are an advantage because you can have the machine cycle through repeated measurements very handily, and it can be all stored on a computer, so it's very attractive to doing deformation monitoring, but we still have the problem with the effects of refraction. Now, some people argue or have suggested that if we do a lot of averaging, then in the average, provided that the conditions are changing from measurement to measurement, then that average should have less refractive influence on it. But that's suggesting then that the way that the averaging and the repetitions are done, that the conditions are going to average out. And part of it depends on the problem. If the monitoring is of a very sensitive structure where the structure itself is changing with a fairly high frequency, then we don't have the luxury of doing a lot of repeated measurements for any one campaign because we're already experiencing a change in the structure. It would only be in where there's a very lazy structure that isn't moving all that quickly, where we can take the time to do, say, repetitions over a day or two for one measurement, and then do the repetitions every year or two or something like
that. We've got a request for the March 2010 exam, question 5, parts A and B.
As I mentioned earlier, an extensometer measures the change in distance but doesn't measure the distance itself. So we have a device that can measure the change in a dimension but only over a very limited travel, say up to somewhere, say, in the order of 100 millimeters, depending on the design of it. So if we want to measure a larger space between 2 points, we have to add on to that, and there are two ways of doing it. One of them is with a tape or with a wire. So we have tape extensometers and wire extensometers, and if we have a series of anchor points that are all about the same distance apart within the travel of this device, then that same instrument wire or instrument tape combination can be used. One of the examples, if you were to Google tape extensometer, is one made by a Solinst company, and it basically is a tape that is perforated every 25 millimeters, well really every inch, but they try to make it into a metric machine. So if you have a variety of lengths, you can choose a particular portion of tape indexed to the perforation within the nearest 25 millimeters to span the proper distance. There's another style where there's an in-bar wire that is used. Oh, sorry, the tape that was used in this extensometer is also in-bar to counteract the effects of temperature changes. There's also one that uses a wire, but the problem is that the wire is a finite length, and therefore you have to either design the series of points to have a lot of them within the movements in order for the same wire to be used, or you have to have a lot of wires. And of course that would be rather inconvenient. Another type of extensometer is basically the same type of difference measuring device, but it's attached to a rod rather than to a tape or a wire, because either the tape or the wire has to be kept under the proper tension, and even under a proper tension, either of them would sag. So they're all right to use, say, from the corners of the gallery or something like that, where it can hang free out in the open. But if you wanted to do something down a borehole, which is a lot more limited in its usable space, then usually a rod is used. And basically what the rod does is it takes the anchor point and brings it out to the end of the borehole or to the surface as a reference. So as the anchor point moves, you would expect the end of the rod at the collar of the borehole to be moving in the same amount. The problem with that, of course, is that unless the rod is free of any outside influences, we have no guarantee that it's free to move back and forth with the anchor point. And this causes a bit of a problem, and there are ways of getting around it, but they're technically quite complicated. The other problem is that in many instances, the borehole goes a fair amount of distance into a structure, and it may or may not be experiencing temperature variations in the same way as a structure. And to give you an example, in a power dam, they may have boreholes going into bedrock from a gallery down below, and they want to figure out whether the point on the gallery is changing with respect to the end of the borehole. So they bring a rod out from an anchor at the bottom of the borehole and measure how the end of the rod relates to the collar of the borehole repeatedly. And supposedly if the anchor point is into bedrock, it's not moving, but the collar might be because it's attached to the structure. So the anchor reference is supposedly then propagated out through the rod. If the rod is not of the same coefficient of thermal expansion as the concrete, and usually steel and concrete have about the same, about 11 parts per million, then you could have an additional influence. And one example that I've seen was where they used aluminium, because if you were to use steel, the steel tends to rust, because in most boreholes there's a lot of moisture and whatever, and rusting isn't so good. Aluminum wouldn't rust, but it has twice the coefficient of thermal expansion. So that means it's expanding and contracting at twice the rate as the concrete, which of course then introduces a rather peculiar picture of things. The other possibility is to use rods out of Invar, which has a very low coefficient of thermal expansion, a tenth less than steel, which usually around 0.1 or so parts per million per Celsius degree. The only problem is that Invar is also can rust, and cause some problems. So we have in situ, meaning that the device stays where it is, or we may have anchor points that are out in the open where we can use a portable instrument of some sort, but the portable ones have to be able to accommodate the different separations.